Our planet, Earth, feels solid and safe beneath our feet. We go about our daily lives, often forgetting the vast, empty, and sometimes hostile space that surrounds us. We are living on a beautiful blue marble, spinning through the cosmos. It is our only home, a tiny oasis of life in an immense universe. But this home is not as secure as we might think. It faces constant threats from space, dangers that are invisible to the naked eye but have the power to cause catastrophic damage. These are not threats from science fiction movies with invading aliens or rogue asteroids, but something much more fundamental and ever-present. They come from our very own star, the Sun. We have built a world that is incredibly dependent on technology. Our lives are powered by electricity. Our communication relies on satellites. Our navigation systems guide planes, ships, and cars. All of this intricate, interconnected network is fragile. It is a house of cards built on the assumption of a calm and predictable space environment. But space is not always calm. It can be violent and unpredictable. A powerful storm from the sun could knock out our power grids, disable our satellites, and send our modern civilization back to the Dark Ages. In 1859, a powerful solar storm known as the Carrington event struck Earth. Today, a similar storm could cause trillions of dollars in damage and disrupt the lives of billions of people. We need to wake up to this silent threat. We must start thinking about how to protect our world. We build storm shelters to protect us from hurricanes and seawalls to protect us from tsunamis. We must now look to the skies and think about how to build a shield for our entire planet. This is not just a fascinating scientific idea, it is becoming an urgent necessity. The primary danger comes from our sun. It is a star, and like many stars, it is active and dynamic. The sun has a cycle of activity, lasting about 11 years, where it goes from a quiet period to a very stormy one. During its active phase, the sun can produce massive eruptions called solar flares and coronal mass ejections, or CMEs. A CME is one of the most powerful events in our solar system. When these solar storms are aimed at Earth, they can cause serious problems. Our planet has a natural defense, a magnetic field called the magnetosphere. This field is generated deep within the Earth's core. It acts like a shield, deflecting most of the harmful particles from the sun. These particles can then interact with our upper atmosphere, creating the beautiful auroras, the northern and southern lights. But a powerful CME can be too much for our natural shield to handle. But they can also induce powerful electrical currents in our power lines and pipelines on the ground, overwhelming and destroying them. So what can we do? How can we protect an entire planet from the fury of its own star? The answer might sound like it comes straight from science fiction, but it is grounded in real physics. We could construct a giant magnetic structure in space, a magnetic megastructure. It would be an engineered shield designed specifically to deflect the most dangerous solar storms before they can even reach our planet. The science behind this concept is based on how magnetic fields work. We could place a huge electromagnet at a stable point in space between the Earth and the Sun, known as the L1 Lagrange point. So, how would we actually generate a magnetic field powerful enough to deflect a solar storm? The answer lies in the remarkable technology of superconductivity. The technology for large-scale superconducting magnets already exists. It is used in medical MRI machines and particle accelerators, like the Large Hadron Collider at CERN. We would need to manufacture thousands of kilometers of high-temperature superconducting cable and assemble it in space. We would also need a robust cryogenic system to keep the superconductors cool enough to operate. The most obvious and abundant source of energy at the L1 point is the sun itself. The primary power source for the magnetic megastructure would therefore be massive solar arrays. This electricity would be used to power the cryogenic coolers that keep the superconducting magnets at their operational temperature. What happens when the very thing you are trying to protect against, a massive solar storm, is about to hit? To ensure the shield remains operational during a storm, it would need a robust energy storage system. For ultimate reliability and long-term operation, the megastructure might be equipped with a secondary power source, such as a compact nuclear reactor. This combination of solar generation, energy storage, and nuclear power would create a resilient and redundant energy architecture. The first step in defending our planet is not the deflection itself, but detection. Fortunately, our magnetic megastructure at the L1 Lagrange point is perfectly positioned for this task. When the sun unleashes a powerful CME directed towards Earth, our shield's sensors would be the first to know. They would immediately detect the eruption, analyzing its size, speed, density, and the orientation of its embedded magnetic field. Knowing these parameters in advance allows the shield's control system to calculate the precise threat level and determine the best response. This would give us approximately 1 hour of advance notice before the storm reaches the shield itself, and anywhere from 24 to 72 hours of notice before the storm would have impacted Earth. But for the shield, this is the signal to prepare for action. Once the early warning is processed and the shield is ready, the main event begins. As the colossal cloud of charged particles from the CME approaches the L1 point, it encounters the artificial magnetic field generated by our megastructure. This is the moment of truth. The shield doesn't act like a solid wall, physically stopping the plasma. Instead, it works more subtly, like a cosmic judo master using the opponent's own momentum against them. The bulk of the storm would be pushed aside, flowing harmlessly around Earth's orbit. Our planet, tucked safely behind the shield, would experience only a gentle cosmic breeze instead of a full-blown hurricane-force solar gale. For several hours, the shield would be engaged in this cosmic arm wrestle, holding its ground and guiding the solar storm safely around our planet. After the main body of the coronal mass ejection has passed the L1 point, the job is not quite over. The megastructure has successfully deflected the bulk of the storm, but its passage leaves behind a complex and turbulent environment. This wake is a region of lower density plasma, but with more complex magnetic fields. It is the aftermath of the battle, a disturbed region of space that Earth will subsequently travel through. The megastructure's systems would continue to operate, but in a different mode. After the primary deflection, the magnetic field might be reconfigured to help stabilize the downstream environment. The goal is to ensure that the environment our planet encounters is not just less dense, but also less chaotic. The data collected during the entire event, from initial detection to the passage of the wake, would be invaluable. Once the wake has passed and the space environment has returned to its normal, calmer state, the magnetic shield can power down its main deflection field to a standby level. The most immediate and daunting challenge in realizing a magnetic megastructure is the sheer scale of the undertaking. We're not talking about building another international space station here. We're talking about a project that's orders of magnitude larger and way more complex. Lifting millions of tons of material out of Earth's deep gravity well would require thousands, if not tens of thousands, of launches. We'd probably need to develop fully reusable super heavy lift launch vehicles, way bigger than anything flying today. An alternative and maybe more practical approach would be to minimize the amount of material we have to launch from Earth in the first place. The Moon, for example, is rich in materials like silicon for solar panels and aluminum and iron for structural components. These parts could then be launched from the Moon's much weaker gravity field, which is a lot more energy efficient than launching from Earth. The heart of the magnetic megastructure is its superconducting magnets, and the core requirement for superconductivity is extreme cold. Maintaining these frigid temperatures for a structure that's kilometers in size, floating in the vacuum of space and constantly bathed in sunlight, is a monumental thermal engineering challenge. So, to keep the superconducting coils cold, the shield would need a massive and highly sophisticated cooling system. These panels, with a surface area potentially spanning many square kilometers, would be designed to radiate this waste heat out into the cold darkness of space. If the superconducting coils warm up even slightly above their critical temperature, they'd lose their superconducting properties instantly. So, the cooling system has to be built with extreme redundancy and be capable of operating continuously for decades without failure, a level of reliability that's honestly far beyond current engineering standards. Assembling a kilometer-scale object at the L1 point, 1.5 million kilometers away from any human support, is just not a job for astronauts in spacesuits. The construction, and the long-term maintenance that comes after, would have to be performed almost entirely by a sophisticated autonomous robotic workforce. We'd need to design and deploy fleets of specialized construction robots, each one built for a specific task, from maneuvering large structural components into place to performing delicate welding and wiring jobs. Swarms of them would work together in a coordinated fashion, following a master blueprint overseen by artificial intelligence and human supervisors back on Earth or at a nearby control station. They'd need advanced AI to navigate the complex construction site, handle components with precision, and work collaboratively to assemble the massive superconducting coils, the structural supports, and the vast solar arrays and radiator panels. Even after the shield is up and running, the robot's work isn't done. A structure this complex will need constant monitoring, maintenance, and repair over its decades-long lifespan. Autonomous maintenance bots would constantly patrol the structure, inspecting for damage, running routine diagnostics, and carrying out repairs. With a fully operational magnetic megastructure standing guard at the L1 point, life on Earth would enter a new era of unprecedented stability and security. The constant nagging threat of a catastrophic solar storm would be effectively neutralized. Industries that are highly dependent on reliable electricity and satellite infrastructure such as finance, telecommunications, and healthcare could operate with a newfound confidence. Our vital assets in orbit, the thousands of satellites we rely on for communication, navigation, weather forecasting, and scientific research, would be shielded from the most extreme space weather. This would not only save billions of dollars in potential damages, but also enhance the reliability of systems that are critical to our daily lives. It would provide a stable foundation upon which we can continue to build a prosperous global future. The potential of magnetic megastructures extends far beyond just protecting Earth. This technology could be the key to unlocking our future as a multiplanetary species, specifically by making it possible to transform Mars into a second habitable world. By placing a magnetic megastructure at the Mars-Sun L1 point, we could create an artificial magnetosphere for the red planet. This shield would deflect the solar wind, effectively stopping the atmospheric stripping process in its tracks. With this protective bubble in place, the atmosphere could begin to naturally accumulate. As the atmospheric pressure increases, liquid water would become stable on the surface once again. Rivers could flow and small seas could form, creating the conditions necessary for life to take hold. The thicker atmosphere would also provide better protection from harmful solar and cosmic radiation for any future colonists living on the surface. It would be the foundational piece of engineering that makes the dream of a green Mars a scientific possibility. The development of magnetic megastructure technology would have a profound ripple effect, creating capabilities that extend far beyond planetary defense and terraforming. The very infrastructure required to build such a shield, lunar factories, asteroid mining operations, fleets of robotic construction vehicles, and super heavy lift launch systems would fundamentally transform our ability to operate in space. For instance, smaller portable magnetic shields could be used to protect individual spacecraft on long-duration missions. A spaceship traveling to Jupiter or Saturn could generate its own magnetic bubble, providing a safe haven for its crew from the constant threat of galactic cosmic rays and unpredictable solar flares. Furthermore, the principles of large-scale magnetic field generation could be applied to entirely new forms of propulsion. A powerful magnetic field could be used to create a magsail, a device that sails on the solar wind. This would allow for propellantless travel throughout the solar system, enabling faster and more efficient transportation of cargo and personnel between planets. The journey from our present vulnerability to a future secured by a magnetic megastructure is a long and challenging one. It is a path paved with immense engineering hurdles, vast economic investment, and a level of international cooperation that humanity has rarely achieved. Yet, it is not a journey into the realm of fantasy. Every step of this grand vision is rooted in known physics and emerging technologies. The choice before us is clear. We can remain passive observers, hoping to weather the next great cosmic storm, or we can become active architects of our own destiny. Building a planetary shield would be our declaration of independence. It would signify our transition from a planetary species to a truly spacefaring one, capable of engineering our environment on a colossal scale to ensure our survival and prosperity. The legacy of such a project would echo for centuries. It would be a gift to all future generations, a silent guardian standing watch over their world. The same technologies developed to construct this shield would unlock the solar system, enabling us to protect future explorers, to bring Mars to life, and to build a vibrant multiplanetary civilization. The construction of a magnetic shield for Earth is the next great leap, the next grand project that will define us. It is a hopeful vision of a future where we have risen to meet the cosmic challenges with courage and intelligence, securing our beautiful blue marble within a fortress of our own making, ensuring that the light of human civilization continues to shine brightly for millennia to come.